Welcome to Chemistry at Honega High School. I'm Brian Brown, and today we'll look at our fifth and final set of notes dealing with chapters 17 and 18, where we'll finish up concepts related to equilibrium. Now, yesterday what we did was we looked at what equilibrium was and how it gets established. Today, what we're going to look at is when you have a system at equilibrium and you do something to mess with that equilibrium. What happens that's predictable and why does it occur? Now, this is what's known as Le Chatelier's principle. Le Chatelier was fascinated by the fact that equilibrium systems were self-correcting systems, and he was trying to study why that happened. And what he came up with was this principle. If a system at equilibrium is stressed, the equilibrium will shift until the stress is relieved. Well, to understand his principle, you need to understand, well, what does it mean by a stress? What does it mean by a shift? And how does that shift then relieve stress? So first off, a stress is anything that changes the forward or reverse rate. Because remember, at equilibrium, we have a rate in the forward and in the reverse that are equal to each other. If we do anything that changes just one and they're unequal, or it changes them in a way that it makes them unequal, then we have stressed the system. So a stress is anything that causes the forward and the reverse rates to be unequal. If it changes the rates but they're still equal, then it's really not a stress. So that's what a stress is. Now, what is a shift to the right and a shift to the left? Well, an equilibrium shift to the right means the forward reaction is favored. So that really means our forward reaction is bigger than our reverse reaction. When that happens, we have a situation where we're going to use up our reactants faster than we're using up our products. So as time goes by, our amount of products is going to increase and our amount of reactants is going to decrease. And eventually we're going to end up reestablishing equilibrium because remember, when they're unequal like this, the fast one is going to use up the components that cause the reaction to occur, and that means its rate is going to drop. The slow one is having its reacting species created faster than it's using them up. So they're going to start to grow, and that means its rate is going to increase. So whenever we have a situation where the rates are not equal to each other, then what's going to happen is the larger one is going to slow down over time, the smaller one is going to speed up, and eventually they'll get to equal again. Well, in the case of a shift to the right, what we're doing is we're describing a situation where the forward ended up bigger than the reverse, and therefore when we reestablish equilibrium, our products will be greater than they were before, and our reactants will be less. So when equilibrium is reestablished, the product concentrations will have increased and the reactant concentrations will have decreased. That's what a shift to the right means. It means forward is bigger than reverse, and as we move towards reestablish equilibrium, we're going to end up with a greater amount of products and a lesser amount of reactants than we had before the shift. Now, shift to the left really means the exact opposite situation. In a shift to the left, what's happening is our reverse is larger than our forward. That's creating an unequal situation. That means our reactant concentrations are going to go up and our product concentrations are going to go down as we reach our new equilibrium. And remember, the same thing is going to happen here. The reverse rate is bigger than the forward, so we're using up products faster than we're using up reactants. Our amount of reactants are going to grow and our amount of products are going to shrink. So on our way to reestablish equilibrium, we end up with a situation where reactants will be greater, products will be less when we reestablish. So in this situation, we call it a shift to the left because the stuff on the left, the reactant concentrations are increasing, and the stuff on the right, the product concentrations will be decreasing. So that's what a stress is, and those are what shifts to the left and to the right mean. Now, when we talk about factors that can affect or stress a system, the primary one we're looking at is concentration. And this is one that is most important because it's really why equilibrium systems themselves are self-correcting, is how changes in concentration causes changes in rates that eventually get you back to equal every single time. Well, let's say we add or we remove a substance from either the reactant or the product side. That's going to change a reactant rate. Now, increasing the concentration on one side of the equation shifts equilibrium towards the other. So fundamentally, if I add a reactant, that's going to shift equilibrium to the right. If I add a product, that's going to shift equilibrium to the left. So add a reactant is going to push equilibrium to the right, but decreasing a reactant would then pull equilibrium back to the left. Because what's really happening here is all about our reaction rates. So when we add a reactant, that's going to make the forward bigger than the reverse. So we're clearly not at equilibrium. And as we reach equilibrium, we're going to end up with more products and less reactants than we had before. Now, when we decrease a reactant, that's actually going to make the forward rate smaller. So now what's going to happen is we have a small forward and we have a larger reverse. So remember, we can increase rates or we can decrease rate. Lowering a concentration of reactant is going to make the forward reaction happen more slowly than it was. That's stressing the system. They're unequal. But now you see a situation where we're favoring the reactants. As we achieve equilibrium, we're going to have more reactants and less products. That's what a shift to the left means. So remember, shift to the left means we're going left. We're favoring the production of reactants, and a shift to the right means we're going to the right. We're favoring the production of products when we reestablish equilibrium. Now, adding a product will do the same thing as adding a reactant, but now we're going to shift the other way. So adding a product would push equilibrium to the left, and that's because that's going to make our reverse bigger than our forward. And as we reach equilibrium, we're going to end up with more reactants and less products. That's shifting to the left. And then when we decrease the concentration or remove a product, that's going to cause the forward rate to be larger than the reverse, because literally what we did was we lowered the reverse rate. And now this is going to be a shift to the right. We're going to favor the production of products over the production of reactants. So as we reach equilibrium, we have more products and less reactants than we had before. So really this is about what we're doing to the forward rate or we're doing to the reverse rate and which way that's going to affect our equilibrium position. Now, notice I use the words push and pull. That's because you can make this a physical situation. So think about whether you're on, if that's our double arrow, so that's what separates reactants and products. We've got reactants over here, we've got products over there. Whenever we had reactants, take your left hand, so hold up your left hand, and when you're adding something, that's a pushing motion. That would be moving the left hand to the right. That's a pushing motion. So literally, you can make this very physical. Get your left or right hand if it's reactants, right hand if it's products. And if you're pushing, you're going to push both hands towards each other. So pushing the left hand would shift it right, pushing the right hand would shift it left. Now removing is a pulling motion. And that means you're going to take your two hands that are in front of you, or technically it's only one hand in front of you. It's either the left or the right. And when you remove, you're going to pull it away. So instead of moving towards the middle, you're going to pull it away and away from your body, which means if it's a reactant, that's left hand. If you're removing, that's going to shift your hand left. So there's a quick, easy physical way to see how this would end up playing out. So think left hand, think right hand. Think push means moving to the center. Pull means moving them away from your body. So let's practice a couple of these. So here is an equilibrium system that's at equilibrium, and we add carbon monoxide. Now what's literally going to happen here, so we're going to look at it the real way and then the shortcut way. If we add CO, that's going to make the forward rate bigger than the reverse rate. And that means we're going to shift to the right. So that's exactly what happens and why it really happens. Now, another way to look at this is our push-pull left-right thing. So we have CO, which is a reactant, that's left hand, and we're adding it, that means push. So you're going to move it to the middle of your body. Notice your hand is going to the right. So it's a quick, easy way to see physically what's going to happen. Increasing the concentration of CH4. Well, if I increase CH4, that's going to make my reverse reaction larger than my forward, and that's going to shift me to the left. So how does it work making a physical representation here? Well, CH4 is a product that's right hand. So if here's my middle, I'm going to hold up my right hand here. And since I am adding, that's going to be a pushing motion. That's going to move in that direction. So that means as I increase CH4, I'm going to move my hand to the left. Now, removing H2. Well, H2 is a reactant, and if I remove it, that's going to affect my forward rate. Well, it's going to make my forward rate smaller. So my forward rate is going to go down compared to what it used to be. Well, that's going to make the reverse bigger. That should shift me to the left. Now, how does it work with left, right, push, pull? Well, H2 is a reactant. So that means left hand. So I'm going to hold up my left hand. Now I'm removing, so that's a pulling motion. That's going to remove away. That's going to go to the left. And then finally, lowering H2O in brackets. Well, what are the H2O in brackets? Remember from a couple of days ago, that means molar concentration. So we're lowering the concentration of the water. Well, that would, as a product, if I'm lowering the concentration of the product, that's going to lower my reverse rate. That's going to make the forward rate bigger if my reverse rate is smaller. And therefore, I should end up shifting to the right. So thinking of it, product, right hand, removing means pulling. My hand's going to move away from my body. It's going to shift to the right. So that is concentration. And remember, it's really about the products and the reactants and what they do to the forward and the reverse rate when you increase or you decrease their concentrations. And that's going to create an imbalance that's either favoring the right or favoring the left. Now, the second thing we're going to look at here is temperature. Now, temperature is looked at as increasing temperature favors the endothermic direction. So what that basically means is if I have some chemical reaction, so let's look at a simple reaction between hydrogen and oxygen to make water. So let's pretend this is an equilibrium system, and to balance it, I'm going to need two waters, which means I'm going to need two hydrogens. Now I've got a balanced equilibrium expression. Now, next would be, well, where's energy? Well, this is exothermic, so that would mean energy is over here. Well, that means the forward rate is exothermic, because remember, when I say exothermic, that's from the forward rate's point of view. Well, that would mean in the reverse direction. So literally, if I'm looking at going in that direction, water breaking apart to make hydrogen and oxygen, I have to add energy to make that happen. So the reverse direction here is the endothermic direction. Now, increasing temperature is then going to favor the endothermic direction more. Now, remember, increasing temperature affects rate. We talked about this a couple days ago. And increasing the temperature increases the rate. So let's pretend I've got a situation where I'm at equilibrium and my two rates are equal to each other. Well, if I increase the temperature, both of them are going to get larger than they were before. So I would expect to see my forward rate getting bigger, and I would also expect to see my reverse rate getting bigger. But remember, in this particular water decomposition reaction we're looking at, it's exothermic from the forward reaction's point of view and endothermic from the reverse. So while both of them are going to get bigger, the reverse is going to get bigger faster. So in other words, it's going to increase more than the forward rate increased. So we've created an imbalance. Yes, technically both of them are occurring faster, but the reverse rate is occurring even faster because that's the endothermic direction. Well, when you have an imbalance like that, the forward rate is smaller than the reverse, you're going to shift to the left. So in my situation up here, increasing the temperature would shift equilibrium to the left. And that means my reactants would go up and my products would go down. So that is what it means by the endothermic direction. Remember, sometimes the endothermic direction is the forward, sometimes it's the reverse. We just looked at a situation where it was the reverse. Now, it's harder for students to sometimes wrap their head around that idea, figure out what the endothermic direction is, and that one's going to increase more. Or if you're doing the exact opposite, decreasing the temperature, that's going to favor the exothermic direction. So it's going to end up with whatever direction the exothermic was being larger, because both of them are going to slow down, but the exothermic one is going to slow down less. So that's just something that sometimes students have a hard time wrapping their head around. So treat it like concentration and push-pull. First, look at where the energy is at in the reaction. So here is a balanced chemical equation, and energy is on the right. This is an exothermic reaction from the forward reaction's point of view, endothermic from the reverse reaction's point of view. And heat or energy is on the right side. So think of right hand. Anything we do to increase temperature, increase heat, add energy is going to be a push situation, and right hand pushing. So right hand pushing, that's going to push to the left. So that should shift equilibrium to the left, which means reactants go up, products go down. Anything in this situation where I'm removing energy, right hand remove, that's pull, that's going to pull to the right. And that's going to end up causing it to go that direction when I take my hand and I pull it away from the center of my body. So that would be a quicker way to see whether you shift left or right than actually following what's happening from an endothermic, exothermic point of view. And I understand that it's more important in general to be able to tell me which reaction is going to end up larger. But in the end, most of the questions can be answered by looking at it and realizing, oh, if I increase the temperature, temperature is right, that's a push, that shifts me left, that's going to go left, I'm going to get the right answer every single time. So treat this like concentration. Now, the one thing that's going to be different here is we could add or remove reactants or remove products. And that would mean I either start with my left hand or start with my right hand. From a temperature point of view, this reaction as written is exothermic. That's always right hand. So I'm going to push and pull with my right hand only when I'm looking at changes in temperature and energy with this reaction. That's fundamentally different than what we talked about with concentration. So to practice removing heat, well, it's right hand removing as a pull. It's going to pull it to the right. Lowering temperature, well, that's the same thing as removing heat. Energy is on the right side, that's a pull. When I pull, my hand goes to the right, it's a shift to the right. So removing heat or lowering temperature would shift equilibrium to the right, making more products at the expense of the reactants. So I'd have more products and less reactants once I achieved equilibrium again. And finally, adding thermal energy. I know it looks different, but we're still talking about adding energy. And energy's on the right, so that is a push. I'm going to push equilibrium to the left, and that means reactants are going to go up and products are going to go down. So that is temperature. Now, let's apply this in one situation to a real world setting here. So we've got a reaction that's at equilibrium between nitrogen dioxide and dinitrogen tetroxide. Nitrogen dioxide is a dark brown colored gas, and N2O4 is colorless. So we can actually look to see what's happening with color to see which way we're shifting, left or right. So let's look at the middle one. In the middle, we've got 25 degrees Celsius, and we're a medium brown color. Now, when we go to a higher temperature, that means adding energy. Notice it gets a darker brown color. Well, if we became darker, that must mean we're shifting in that direction. We're shifting towards the brown. Well, think about it. Where is energy if adding it is going to shift to the left? Well, that would mean energy has to be over here. So based upon the visual evidence, it looks to me like this must be a situation where the energy has to be on the right side of that equation based on the visual evidence. When it got hotter, it got darker brown, and when it got colder, it ended up shifting to the colorless side. Well, that would only be true if energy, based upon the evidence, were written on the right side. So from the forward reaction point of view, this would be classified as an exothermic reaction. And our visual evidence supports that. So if we actually look up this reaction and look to see where energy is, you'd see it's exothermic. Energy would be on the right side of this equation. So increasing temperature would shift me left, making it darker brown. Removing energy or decreasing temperature would shift it right, making it a more colorless solution, so a lighter brown color. And that's exactly what we see. Next thing we're going to look at is pressure volume. Now, so far in both situations, every time we change concentration and we change temperature, it shifted us either left or right. But with pressure volume, there will end up being situations where it doesn't shift us at all. So this is one where we have increase, decrease, left, right, or we have no change whatsoever. Now, increasing the pressure or decreasing the volume, fundamentally they're doing the same thing. When we increase the pressure, picture holding your hands and making an imaginary container, and picture increasing the pressure on that container. You would be pushing your hands closer together. Well, that's like a decrease in volume. So increasing pressure or decreasing volume are going to favor the side of the reaction with fewer gas particles. Well, take your hands and hold them a little bit apart, and then increase the pressure, push them closer together. You can see the volume decreasing, and you can see the fact that you have less and less space between your hands. So if you could shift equilibrium in a direction that took up less space, and remember, what fills a container are gas particles, not solids and liquids. They're going to sit together clumped on the bottom. So the only thing we're worried about here is how many gas particles do we have on the left and how many gas particles do we have on the right. If there's a different number of gas particles on the two sides, pressure volume changes will affect equilibrium. If there's not, if they have the same number of gas particles on each side, yes, when we increase pressure, we're decreasing volume, so to speak. But we don't have a difference in the number of gas particles, so it's not going to affect equilibrium at all. So increasing the pressure is going to favor the side with less space, which would be the side with fewer gas particles. And then the opposite, decreasing pressure, which would be like increasing volume, that's moving your hands farther apart. That would favor the side with more gas particles. So really, it's about counting gas particles. So the first thing we need to do is look at how many gas particles on the left. On the left, they're both gases, so they're both going to count towards our total. CO, well, in the balanced equation, there's 1, and H2, there's 3. Well, that's a total of 4 gas particles. On the right side, they're both gases, so they're both going to play a role. I have CH4 and H2O, coefficient of 1 in each case. That means I've got a total of 2 gas particles. So when I increase the pressure, remember, physically take your hands and make an imaginary container and then increase the pressure on it. Push them closer together. You're going to see you have less space. That's going to favor the side with less space, which is the right side. So in this equilibrium system, if I increase the pressure, that's going to favor the production of products at the expense of the reactants. So I'm going to shift to the right, my products are going to go up, and my reactants are going to go down. Now if I increase the volume, well, that's like making more space between my hands. That's going to favor the side that has more space, which would be the left. So increasing the volume or decreasing the pressure is going to favor the left side. So my reactant concentrations would go up, my product concentrations would go down. Remember, it's like a teeter-totter. When one goes up, the other has to go down. Lower the volume, well, just pitch your hands and pitch your lowering volume. That's moving them close together. That would be the right side, the side with fewer gas particles. Now let's look at a different situation. We do the same thing. We start by counting, but now they're not all gases. So on the left side, AC is a gas and there's one, but B2 is a solid. Doesn't really matter that there's three. Those aren't gas particles. So on the left, I have a total of one gas particle. On the right, I know I have a bigger substance, AB4, but there's still just one AB4 and it's a gas. So that's going to contribute one. And B2C is also a gas and it's got a coefficient of one. So that's also going to contribute one. We have two gas particles on the right. So increasing the pressure, remember, hold your hands, make an imaginary vessel, and then picture pushing them closer together as you increase the pressure on it. That's going to take up less space. It's going to favor the left in this case. So last time the fewer gas particles are on the right, we shifted right, we increased pressure. Now with this system, we're increasing pressure, and now we shift left because the left side has fewer gas particles. Now let's look at the last one. Notice they're all solids. So we have 0 on the left, 0 on the right. So if I increase the pressure, which side's it going to favor? Well, increasing the pressure is pushing your hands closer together. You've got less space, but both of these have the same in terms of the number of gas particles. So it's not going to do anything. And remember, if they were both 2's, it would be the same answer. No change. Simply because there isn't a difference between the two. So in this particular case, increasing pressure is going to have absolutely no change on our equilibrium system. In other words, we didn't stress the system. And that means we're not going to change rates and make them unequal. And that means we're not going to change our concentrations of products or reactants. Now, the last one we're going to look at is the addition of a catalyst. Now, you may remember, and hopefully you do, that adding a catalyst speeds up a reaction. Well, it actually speeds up both reactions, because if we look at the energy diagram, what a catalyst did is it made a low energy pathway. Well, that's going to lower the energy of activation of both the forward and the reverse rate by the exact same amount. So it has no effect on equilibrium because it speeds up equally both reactions. So remember, our rate is going to be tied to our energy of activation. And the energy of activation in the forward was this amount. And the energy of activation of the reverse reaction would be that amount. Well, when they both go down to there, you've changed them both in the exact same way. They're both going to be sped up. They're still going to be equal. We haven't stressed the system. So, quick review of ideas here. We have this simple reaction of A plus 2B yields C plus D. What would happen to equilibrium if the concentration of A was increased? So what we're basically doing is adding some A, so this is going to go up. Well, that's going to increase my forward rate, and my reverse rate at the beginning is going to stay the exact same. That's going to create an imbalance. That's going to shift equilibrium to the right. So I'm going to get a shift to the right. Well, what would then happen to the concentrations of C and D if I'm shifting to the right? Well, remember, shift to the right means the forward reaction is bigger, and we're favoring the production of products. So we're going to make our products faster than we use them. That's going to increase the concentrations of C and D. Now, we know what happened to A. We threw in A in there. So yeah, A is going to go up a little bit. But what's going to happen to B? Well, think about it. If we make C and D, it has to come at the expense of A and B. And while I added some A, so when I used it up, I'm still going to be more than I was before, but I didn't add any B. So in order to make C and D, I had to use up B. That means B is going to go down. So this is the type of thing you should be able to answer. What's the shift, and then what happens to the other substances? And in the case of concentration, you're going to be looking at the other reactants and products, because obviously the one you added or lowered is going to be raised or lowered in the course of the reaction. But what happens to the rest when you get that shift in equilibrium? That's what we're really looking at. And that ends our notes over equilibrium shifts and what they mean. I do want to mention one last thing. What would happen to the concentration of A? Well, really, we don't know where it's going to end up, other than the fact that I know I added some and I used some, so I'm probably going to be higher than I was before. But I don't really know because I did both. I added and I used. So you're not going to be asked about A hint. And that finishes our notes.